So, Xianglong, are you ready?
Yeah, I'm ready.
Okay, great. So we're very happy to have Xianglong Ni from UC Berkeley today, and he's going to tell us about perfect ideals of grade 3 with small Betty numbers.
Great. Thank you very much for the introduction, and also thank you for having me here. I'm very excited to share some new developments in understanding the structure theory of these perfect ideals of grade 3. So everything I share today is based on ongoing joint work with Lorenzo Guerreri and Yosha Wyman. And throughout, I'm going to be working all over the complex numbers. In fact, a lot of the results we expect to be true more generally, say for an infinite field, but so far the theory has been developed over C, so I'll just impose that assumption throughout. For the first part of the talk, where I go for background, this assumption is very overkill. A lot of these classical results hold in much greater generality, of course. But just to avoid the distraction, I'll just impose this assumption throughout. So in fact, I'll be working throughout over a regular local C algebra. And our goal is to understand the structure of perfect ideals of grade 3. So I is a perfect ideal of grade 3. So I should define what these objects are. The grade of I is, by definition, the I depth of R. But with my assumptions on R, this is just the same as the codimension. So if you prefer, you can just think of it as that. Right. And then the condition that I is perfect, there are a few ways of characterizing this. Perhaps the most standard is to say that R mod I is Cohen-Macaulay. But since secretly this project is really a project about free resolutions, I'm going to prefer to use a characterization in terms of free resolutions. And so this is going to be equivalent to the Alexander-Groos form, that the projective dimension of R mod I is equal to the codimension of I. So in our particular setting, what that means is the minimal free resolution of R mod I will have length 3. So our B0 equals 1, of course. And just to introduce some terminology, we'll say, and so B0, B1, B2, B3, these are the ordinary Betty numbers of R mod I, and sometimes they'll be kind of sloppy and just say of I. And we'll also say call this the format of the resolution F. If F is this. Right, so the format is just the sequence of ranks of the free modules. And we give them a new name because, in fact, a lot of what's done in this topic is over. We don't require that the resolutions be minimal in general. So it's helpful to have a separate notion that doesn't coincide with Betty numbers always. So before I tell you about the story in grade 3, I want to say what's known in grade 2. And the situation in grade 2 has been well understood for a very long time. So right, and it goes back to famous theorem of Hilbert-Birch. First established by Hilbert in the 19th century for polynomial rings, and then later vastly generalized by Birch to arbitrary rings. And it completely characterizes the structure of free resolutions of length 2 of sibling modules. Right? So if we have a free resolution of this form, then D1, right, the generators of this ideal I, is just given by some non-zero divisor times the matrix of maximal minors of D2. Now, in particular, if I is a perfect ideal, then this non-zero divisor better be a unit. So in particular, perfect, this is a unit. Right, so this gives a complete description of all perfect ideals of grade 2. And an equivalent way of stating Hilbert-Birch, although actually, well, I'll say something a little bit stronger, but one way of rephrasing Hilbert-Birch, right, is you can define the ring, this polynomial ring, in indeterminates xij and one more indeterminate y. You can define the complex where this is the generic matrix and the variables xij, and then here you have the same recipe that's what's given here. So this is y times n-1 by n-1 minors. Right, and with this setup, the statement of Hilbert-Birch is that given any free resolution of format 1 and n-1, there exists a unique map from R universal to R, specializing this F universal to F. Now, what's also true is that, in fact, this F universal is itself exact, so it is legitimate to call it the universal example. So the fact that there exists this map translates to the existence of, like, the way that we can interpret this is giving a structure theorem for these resolutions of format 1 and n-1. And the fact that this universal example is itself acyclic is a way, in effect, of capturing that this structure theorem is the best possible, right? Because any structure theorem that you can come up for this class of ideals must already be present in the universal example. So that's the place to look if you want such results. So with that in mind, one might try to continue this project, right, to longer free resolutions. And this was sort of officially proposed by Hochster in 1975 at the CBMS conference, the idea of looking for these universal free resolutions for longer formats. Right, and he also handled the case of length 2 when B1 is, or B0 is greater than 1. So the case of module formats of length 2. Now, not so long afterwards, in 1984, Bruns showed that there is a slight issue with this project, which is that it's a little too much to ask for uniqueness, in fact. We cannot require that the map from this universal object to our particular one of interest be unique. So it's too much to ask for uniqueness. Specialization. All right, so define the generic pair instead of the universal pair. Just dropping the uniqueness requirement. Such an object always exists. Right, so in this paper, Bruns showed that if you require that the map, the specialization be unique, then actually, in some precise sense, the best result that you can hope to get is the first structure theorem of Buxbaum and Eisenbud. But if you want the a generic example for free resolutions of length longer than 2, they need to drop this uniqueness requirement. And once you drop the requirement, then it's fine, because in that same paper, he shows that these objects do exist. However, the proof is, it actually is constructive, but it's not constructive in a very concrete way, I guess, which is, right, if you go back to, say, Hilbert-Birch, it's the content, the substance of Hilbert-Birch is less that this R universal exists, but more what explicitly it is, right? The interesting part of Hilbert is R universal is explicitly this and F universal is explicitly this. So one would like to understand more concretely what this generic example looks like. And this is what Lyman set out to do for length 3. But before I describe that, I'm going to give not a proof, but sort of just a heuristic argument for why this uniqueness is too much to ask for. And the reason I want to do this is because it's actually going to be important for a lot of the later examples. So if you consider a free resolution of length 3, say a cyclic module, then it is a fact that any such free resolution has the structure of a graded commutative differential graded algebra, in fact lifting the multiplication on the Tor algebra. And the way you can define this is just by playing it by ear, basically, right? If you want to define the multiplication on two elements of degree 1, this is going to be skew commutative, so it's a map from wedge to F1 to F2, right? And if we want this map to satisfy the Leibniz rule can be stated as a commutativity of a certain triangle right here, right, where this map is defined in terms of D1. Okay, so we just define the multiplication wedge to F1 to F2 by lifting this map through D2. But as you see from this process, this lifting is not unique because D2 itself has a kernel given by D3. Now, once you've taken the multiplication from wedge to F1 to F2, the rest of the multiplicative structure actually is completely determined. But at this first step, to define wedge to F1 to F2, there's non-uniqueness. So let me record that. Right, so the multiplication is not unique. And the non-uniqueness is recorded by a map from wedge to F1 to F3, so an element of this. Okay. Now the multiplication is perhaps familiar, but you can give other examples. For example, let's say once you've defined the multiplication, it's possible to define a map like this. You don't have to worry so much about the particulars. This is just so I can write down another example, the wedge to F3 to F3 tensor F2. This is the Schur complex on D3, then finally with S2 D2. And so I claim there's a way of constructing a map from wedge 4 F1 by lifting an appropriately constructed map like this to this. And then you see that the non-uniqueness of this map is wedge to F3 dual, or wedge to F3 tensor wedge 4 F1 dual. Okay, so how does this relate to this earlier point about why it's too much to ask for uniqueness of centralization? Well, if we were to have this generic example, right, then in particular in the generic ring, R generic, the entries of this map exist. And then the specialization from R generic to R would send those variables to a particular choice of, say, this map for my given resolution, right? But the point is that there's no canonical choice of multiplication. So you don't expect there to be a unique way of specializing these variables to your given ring R. And likewise, the same deal here, right? Which is that the entries of this matrix exist in the generic ring, and the map from the generic ring to R amounts to, well, part of it will amount to picking a particular choice of this lift, but there's no canonical choice, which is why the non-uniqueness is sort of necessary. But again, this is not like a rigorous proof. This is just a holistic, heuristic argument of why this is sort of expected. Okay, so in fact, what I'm doing here, it's not exactly the systematic way that Lyman constructs the generic ring for pre-resolutions of like 3, but it's related. And so let me just now say, so from 1989 to 18, construction of the generic pair for formats B0, B1, B2, B3. So resolutions of length 3. Now, I'll explain this sort of like funny range of dates in a bit. So this is like the first paper in 1989 and then all the way up to 2018. So in the original paper, the construction was already laid out. but some features of it were not able to be proved. For example, the fact that this generic resolution was actually acyclic. Now, the idea is to construct generic, systematically taking into account the non-uniqueness of higher structure. So I'll just give an example. So for a particular sequence 1562, the non-uniqueness is actually recorded just by the two examples I already gave. So non-uniqueness there's F3 tensor wedge 2 F1 dual, and there's L2, which is wedge 2 F3 tensor wedge 4 F1 dual. And that turns out to be it. This is somehow the only quote unquote necessary non-uniqueness of the map from the generic ring to R. Now, what Wyman shows is that this is actually a graded Lie algebra. There is a bracket from L1, comma L1 to L2. Now, it was not until much later, and that's the reason for this range of dates, which is around like 2010, that Wyman realized that this Lie algebra, this graded Lie algebra over here, is actually just a part of a much more well-studied Lie algebra. So now let me show you what that is. This is just part of a larger Lie algebra. So all right, so I claim this is a well-studied one, but what is this? It may not look so familiar when presented in this way, but I claim this is actually just E6. This is the Lie algebra E6. All right, and I'm going to draw the diagram E6 in a sort of funny way that I'll explain in a moment. And the part that I'm not going to explain is that when you have, okay, the Lie algebra E6 is actually Z6 graded, and if you single out a vertex on the Dynkin diagram, then you can coarsen that to a Z grading, and what's displayed here is in fact the Z grading induced by singling out this vertex on the Dynkin diagram. But that's the part that you can just take on faith. There's right, there you have this Lie algebra E6, very well known, and then there's a certain Z graded decomposition of it that results in this. And then this so-called defect Lie algebra is just the negative part of E6 in this grading. So what Wyman shows, so okay, let me write down what I sort of just said, which is that, so L is a negative part of E6 in a certain grading. And the idea is that the non-uniqueness of this map, so given a particular free resolution, for R, the non-uniqueness of this map is given by L tensor R. Right? So L is this complex Lie algebra, and then tensor with R, I get the non-uniqueness of this map. Right, so this is abusive notation. Over here, I really should have wrote define, and for this example, Fi is C to the Bi. Okay. All right. Any questions so far? All right. So what Wyman shows is that, okay, so in the original 89 paper, it's already shown that this defect Lie algebra L acts on the constructed ring R generic by derivations. But in fact, the entire Lie algebra, in this case E6, also acts by derivations. So say that now, not only does L act on generic by derivations, so does this larger Lie algebra G, which in this example of 1562 ended up being E6. So what is G in general? So in general, here, G is the Katsbudi Lie algebra associated to the graph. So I'm going to make a T-shaped graph where there's B0 nodes on the left arm, B3 nodes in the bottom arm, and then B1 minus 1 nodes across the entire top. So for example, right, 1562 gives me 1 node on the left arm, 2 nodes on the bottom arm, and then 4 nodes across the top. So that gives me the diagram E6. Okay. And what the picture from before was is that if you look at the grading induced by this vertex, then L is the negative part of that grading. So the particulars of this whole story are not going to be so essential to what I want to share today, but right, just taking a step back, it's very astounding that just by studying the structure of free resolutions of fixed size, of fixed format, that we get the appearance of these Katsbudi algebras. Now, Katsbudi algebras are quite mysterious in general, but the point is that in the event that this is a Dinkin diagram, then the Katsbudi algebra G is just the familiar simple complex algebra G. And those will play a particularly special role in this whole story. So the theorem. So, right, so this constructed ring R generic is Noetherian if and only if the format corresponds to a Dinkin diagram. Okay, but now let's return to this idea here, right? Which is that I have the action of this Lie algebra G on this generic ring constructed by Wyman. So inside the generic ring, we can look at the entries of differentials di. And what I mean by that is, right, the generic complex of generic, its differentials, the entries are some variables in R generic, right? So I'm going to look at those variables in the ring. So, all right, for example, D3 is a map from F3 to F2, so its entries are actually an element of the tensor F2 dual tensor F3, D3, D2, D1. Then here we have C tensor F1. Right, so these are the representations of GLFI inside of this ring, spanned by the entries of these differentials. Okay. But since I know that this Lie algebra acts on the generic ring, I can ask, what are the representations of G generated by these differentials? Now, the defect Lie algebra, which is a negative part of G, actually acts trivially on these three representations in G, which is to say that what I've listed here is actually the bottom graded component of the representations of G. So the entire representations look like this. For this one, the next component looks like F2 dual tensor wedge 2 F1. The next one is F2 dual tensor F3 dual tensor wedge 4 F1, and so on. And by the way, this is the reason why I talked about the multiplicative structure in this other structure map earlier, because just as how this representation gives the entries of the differential, this one gives the choice of multiplicative structure, and this one gives this other structure map that I had defined before right here. But okay, that's just a particular example. It's not going to be so important. Like the precise definitions of these structure maps are not going to be important for what I want to talk about today. Okay. Now, for the next one, you have this. And here you have this. And I'm going to call these WDI. So WD3 is this, WD2 is this, WD1 is this. And so this is just WDI is the G representation generated by entries of DI in our generic. Right? And what I'm displaying above is what I claim their decompositions look like. So particular in the bottom graded piece, we see the differentials, and the next we see a choice of multiplicative structure, and so on. So we'll use this to define the higher structure maps, right? The idea being that they're higher structure maps because in the bottom we see the differentials, and that these are higher up in these representations. So we define W3, so define WI to be the restriction. Well, okay, I should probably write it this way. Okay. Given F a free resolution of format 1, B1, B2, B3, define the higher structure maps to the restriction to WDI inside of the generic ring. Right. Oh, I guess given F at a choice of specialization and a choice of okay, but in particular, I want to view them this way. I want to view W3 not as a map from this to R, but rather as a map from this to F2. So W3 is a map from F3 plus wedge 2 F1 plus ... to F2. So the first component of this map is a differential, the next component is this multiplication, and so on. And then likewise, we'll define the W2 to be a map from F1 dual plus F3 dual tensor F1 plus ... and W1 oops, to R. Okay. So now the question is, all right, I probably don't need, I'm going to try and sell these structure maps to you. Like, I'm going to convince you why you should care about these structure maps. The first two maybe don't need convincing, right? In the bottom piece, you see the differentials. Of course, we care about those. The next piece, we see multiplication. And I think reasonably enough, you care about those. But then beyond that, the higher structure maps are very mysterious, right? So a natural question is why are they interesting? Why are they useful? And the answer that I will propose is, well, one answer that I propose is that they will give a very nice picture for understanding the behavior of linkage. And that's going to be the next topic that I want to talk about. Okay, so now we're going to switch gears and talk a bit about linkage. So for those unfamiliar, I'm just going to give like the very basic algebraic definition of linkage, which is that if codimension I is C, then and k and I generated by a regular sequence of length c, then we say the colon ideal j, which is k colon I, which is by definition all f and r such that fi is contained in k, is linked or directly linked to I via k, right? And we will write I tilde j, maybe with a k to emphasize this through this regular sequence k. All right, so this whole story is a story about free resolutions. So the main result on linkage that I'm going to use is a result that tells us it's actually possible to write down a free resolution of the linked ideal given a free resolution of the original one. And this is a result that appears in Peskin-Spiro, but there it's attributed to Ferrand. So maybe write it like this. The theorem is due to Ferrand, and it appears in Peskin-Spiro 74. And so if I is a perfect ideal, and f is the minimal free resolution of I, then a non-minimal free res, or I guess R mod I, of R mod the colon ideal is given by the dual of the mapping cone of the comparison map from the causal complex to F. So on the one hand, I have F, which will, by the way, have length C, right? Because we're assuming that I is perfect. And then I'll have my regular sequence. And then on the bottom, I have the causal complex. Oops, this is a C, not a 3. Although the case of interest will be for C equals 3. This one's isomorphic to R, right? And then you take the dual of the mapping cone, which means the resolution will look like this: FC dual plus RC, then so on, right? So the first free module here is the dual of these two, and the next is the dual of these two, and so on. Now, there's some evident non-minimality here. For example, at the very end here, these will cancel out. And if you take minimal linkage, then this will be a split inclusion. So there'll be more cancellation here. You can cancel out these C factors of R with C copies of R up here, if this is a split inclusion. Right, so that's going to be the case that we're interested in. So I'm going to write that down. If split, so if link is minimal, which is to say I'm taking minimal generators to link with, this is split inclusion. So I think I should take the break in around like 5 minutes from now. So I'll say a few more words about linkage, state the main result on linkage, and then we'll take the 5-minute break. So what this result tells us is that, well, let's see what it says in the case of codimension 2. Right? So if C equals 2, codimension is 2. Well, okay, I already used C for codimension. C equals 2. Then the free resolution of R mod I looks like Rn minus 1, Rn, R. And if I take a minimal link, so here I have a split inclusion of R2 into Rn, the causal complex just looks like this. And the dual of the mapping cone, after I cancel the evident non-minimality, looks like this, right? This is going to cancel with 2 factors here, and this will cancel with this. So what I'm left with is just a free resolution of format 1 n minus 1 n minus 2. So what does that mean? This means that in the case of codimension 2, every time you do a minimal link, the total Betty number of your ideal decreases. And every time you do this, it gets the Betty numbers decrease. So after a finite number of steps, you reach Betty numbers 1, 2, 1. And a perfect ideal with Betty numbers 1, 2, 1 is a complete intersection. Right? So this shows any I and R perfect of codimension 2, then I can do a sequence of links to reach a complete intersection. And the term for this is that I is in the linkage class of a complete intersection, which is abbreviated as saying I is Lichi. Now, this argument does not work for codimension 3, but it's interesting to see what it tells us for codimension 3. Right, so if C equals 3, then I have a free resolution that looks like this. And then I draw a comparison map from the causal complex, which will now have format R33, 1331. And if this is a minimal link, then I can make some evident cancellation when I take the dual of the mapping cone. And so this will cancel, and this will cancel with 3 up here. And what I'm left with is a free resolution that looks like, that is format 1, B3 plus 3, B2, B1 minus 3. And if you do it again, you actually end up going back to B0, 1, B1, B2, B3. So in other words, when dealing with perfect ideals of codimension 3, the result tells us that we kind of just expect it to flip back and forth between two types of Betty numbers. Now, well, we can make some observations. So like when do we actually get a drop? Right? When do we actually get simplification and drop in total Betty number? Well, it happens when units appear in one of these two vertical maps. Right? So first of all, if a unit appears here, that means I end up with the unit ideal, which means that K was actually equal to I. So observation, if wedge 3 R3 to wedge 3 F1 to F3 is non-zero mod M, then I equals K. And then if wedge 2 R3 to wedge 2 F1 to F2 is non-zero mod M, then I get a drop in Betty number. After link. Right. So it's of particular interest to see when this happens. The unfortunate news is that this is not even guaranteed to happen at all at any stage. So for example, what I mean by that is that there are perfect ideals of codimension 3 that are not in the linkage class of the intersection. Right? And from this picture, what it means is that it's possible that you just keep doing this and you go back and forth between two formats and never get a drop of Betty number. So there are perfect ideals of codimension 3, not Lichi. And you can take very easy ones. For example, you just take the square of the maximal ideal in three variables. Okay. And the Betty numbers of this ideal turn out to be 1, 6, 8, 3. And in particular, if you draw the T-shaped graph associated to this format, you get something which is not a Lincoln diagram. So now this will lead us to, I'll state the first of two main results, and then we can take the break. So theorem, so this is the result in linkage. So this is the Lichi property of Lincoln perfect ideals. All right, so if I is perfect of grade 3 and has Lincoln Betty numbers, and I'll just say explicitly what this list is. So for type Dn, you get two cases, 1 n 1, or 1 for n minus 3. For E6, you get 1, 5, 6, 2. For E7, you get 1, 6, 7, 2, or 1, 5, 7, 3. And for E8, you get 1, 7, 8, 2, or 1, 5, 8, 4. Right, so if my ideal is perfect of grade 3 and it has Betty numbers in the list that I've just written, then it's Lichi. So there's one other main result that I want to share later on, but the reason I want to do this one first is one, because it's easier to state, and actually because as we investigate this result for a bit, it'll make it easier for me to motivate the next result. Yeah, maybe we can take a break for 5 minutes now.
All right. So yeah, let's take a 5-minute break, maybe start at 17 past the hour. So any questions for Xianglong in the meantime?
I just wanted to say hello.
Oh,
Can
hey.
you hear me?
Yeah, I can hear you.
Yeah.
Where are you right now?
I'm in an airport in Boston.
All right.
Okay. So let me first make a note regarding a question that was asked, which is that this theorem is actually sharp, right? And it's sharp in the sense that, remark, in Stinson, Lyman 20, it is shown that perfect ideals, that for all other possible Betty numbers, there exists a perfect ideal with those Betty numbers that is not Lichy. Right. And the idea is that they construct a few examples and then they show that you can get to every Betty number by linking upwards, basically. Now, what I want to do is I want to illustrate or do a demonstration of how this result works in a very, very explicit example. So I'm going to take the monomial ideal x squared y squared z squared xz xy in a polynomial ring in 3 variables, applies to the maximal ideal. I claim that its Betty numbers are 1, 5, 6, 2. So as a consequence of this theorem, it will follow that this ideal is in the linkage class of the intersection. So let me show you what the free resolution looks like. So here what I've displayed on the top is the differential D3 of the resolution of my monomial ideal. And this is the dual of D2 for the resolution of my monomial ideal. And the other 2 matrices are what I get for the resolution of the linked ideal using this result of Ferrand that tells me that I can write down the mapping cone, write down of the comparison map in the causal complex, and use that to write down differentials for the resolution of the linked ideal. But as you see from this, right, from the mapping cone picture, the differential D3 of B, which is shown in the bottom, is just part of the differential D2, right? But on the other hand, the differential D2 of B, it's not entirely visible just from D3 because there's also that vertical map in the ladder coming from the comparison from the causal complex to A. And that vertical map can be viewed as part of the multiplicative structure on A, right? It's this map from wedge 2 R3 to wedge 2 F1 to F2. So in other words, if I want to understand how to get these differentials of the resolution linked ideal, I should take a look at the multiplicative structure on the original resolution. And what you see from this is, okay, now I can write down explicitly the differentials, right? I was already happy with D3, and then D2, you see the remaining parts here just come from part of the multiplication on A. Matrix I just revealed up top is the multiplication wedge to A1 to A2. Okay, so in particular, I want to call your attention to the presence of this unit in the multiplication, which shows up here in the differential of B. And what does that mean? It means that the ideal that my original ideal is linked to actually has lower Betty numbers, right? Because the resolution that I write down from the dual of the mapping cone construction, I mean, sure, there's the evident non-minimality that I already threw out, but there's another one right here, right? So like the differential D2 is not minimal. So instead of being linked to 1562, it's actually linked to 1452. Okay, so the presence of a unit in wedge 2A1 to A2 is a witness of the fact that the Betty numbers drop after a link. but you can't always find a unit there. So maybe one would like to also know, okay, if looking at the multiplicative structure allows us to see, I guess, one step into the future in regards to linkage, what do we need to know in order to see 2 steps into the future? Or to put another way, what do I need on the original resolution to be able to write down a choice of multiplicative structure on the resolution of the linked ideal? And so I'm going to show you now that a lot of the multiplicative structure can already be written down using what the differentials and multiplicative structure on the original ideal, namely, I guess, all of this, right? And all of this. But there's some extra stuff, right? I don't see the entire story just from the differentials and multiplicative structure. So what more do I need? And this question was answered by Avramov, Custon, and Miller, who showed that if you can define a higher structure map, well, 2 higher structure maps, which they call X and Y, on the original resolution in terms of the differential, well, by doing an appropriate lifting of the differentials and multiplicative structure on the original map. And as it turns out, the structure maps, X and Y, that they define, they're not exactly the same as the structure maps that you get from Wyman's generic ring, but they're very closely related. So I'm not really lying when I say that, in some sense, the maps I just introduced at the top matrices are the structure maps of Avramov, Custon, and Miller. And once I have them, I can fully write down the multiplicative structure. All right, so this is from here. I guess all of this is from here. Right, and then this is from here, and then this gives me the last column there. Okay. So now I can see 2 steps into the future because if I have these 3 structure maps from the original resolution, then I can see 2 structure maps, the linked one, and then I do another step, I can at least see the differentials in 2 steps in the future. Right? But the problem is this is still, I can only see finitely far into the future because at every step I'm paying more and not getting back as much in return, so to speak. So you might continue playing this game and then ask, well, what if I want to write down the maps X and Y for the resolution B? What do I need to know about the resolution A to achieve that? And I claim that, what if I want to know these maps? What do I need to know about the resolution A to achieve that? I claim that it's given by this next part here. And so these maps X and Y on the, I guess, a lot of this already comes from the existing maps, right? I guess most of it does, in fact, right? This one comes from here, and the rest of this comes from here. But then these are not yet visible from just differentials, multiplication, and X and Y on A. But once I introduce this next structure map, then it is visible. And the same thing is true for the bottom one, although I guess I didn't actually need it for the bottom one. Okay, it seems like there's not really an end in sight to this process, right? You just keep doing this. So if you want to know more about B, then you have to pay a bigger price for A. You need to know more about A, and so on. But see, this is why the Dinkin formats play a particularly distinguished role in the theory, because what I'm writing down here, these structure maps that you get from Lyman's generic ring, right? They're representations of G. And if G is a finite dimensional complex simple Lie algebra, these representations are also going to be finite dimensional. And in fact, the punchline of this is that this process stops here. So once you know all these structure maps for A, you don't see finitely far into the future in regards to linkage. You know the entire future of linkage, the minimal linkage for this ideal, right? So here, the point I want to emphasize, right? Do not bother staring at like particular entries of these matrices. That's not so interesting. What I want to emphasize, the top 2 matrices are the same. The bottom 2 matrices are the same. They're the same 6 by 27 matrix, just broken up in different ways. And breaking them up one way can be interpreted as higher structure maps for A, which resolves I, or R mod I, and breaking them up the other way allows us to interpret them as structure maps for B, which resolves R mod J, the linked ideal. Okay, so that's two pictures. There's a third one, right? So the 2 pictures show you how D2 and D3 are related to each other for the 2 resolutions. But in some sense, the third one, which shows you how D1 is related of D1 of A is related to D1 of B, is the most important one. And the reason it's not displayed here is partially for cosmetic reasons, which is that the existing matrices fit nicely onto the page as 6x27 matrices, but the one for D1 is actually a 1x78 matrix. So I'm going to display on the next screen, but it's going to be already broken up. Right, so this is a 1x78 matrix that I've broken up in a way to show you that okay, on the bottom piece, I have the differential. Right, so here in red, I have the differential for the resolution of I, D1, and then above that, I have higher structure maps. Right, this all collectively, this 1x78 matrix is the map I was calling W superscript 1 earlier. This map is W superscript 1. So at the bottom, I see D1. In the next step, I see the multiplication, which through A1 to A3. And I see more mysterious structure maps higher up in this picture. Okay, but going back and looking at the previous picture, I see that if I want to understand linkage, I want to understand both of these two decompositions simultaneously. So what I'm going to do next is so far I've taken this 1x78 matrix and broken it up with respect to the grading that lets me view this as higher structure maps for A. But I'm now going to break it up in another grading. So let me notate this. What's going on here is that here I have E6, and then I have two gradings. Okay, this one is red, this one's the red grading, and this one's green. This one's the green grading. I'm not going to talk about the particulars of how this works. Just take my word on faith that if you have, say, E6, the Lincoln diagram, and you single out two nodes in the Lincoln diagram, then you get a bigrading. And the particular mechanics of how that works, I don't really want to get into. But what I'm displaying here is a bigraded decomposition of the 78-dimensional representation of E6. Okay, so what do I see? In particular, as a result of looking at this bigrading, this R5, right, A1 is R5, got broken up as R3 plus R2. And the R3, I see this XZ, Y squared, Z squared, which is not what I want to see. I want my regular sequence to be there. Right. So this is a little problematic because I would like my regular sequence to be in that R3, but I can fix this because I can just act on this entire picture by an appropriate element of GLA1. If I act by an appropriate element, I can make it so that the regular sequence I want to link with appears in the bottom left corner, and I'm going to do that. Okay, so between the left picture, this picture, and the next one, all I did was act by an element of GLA1, which effectively acts on each row of this picture. And after doing this action, I see my regular sequence, x squared, y squared, z squared, in this bottom bigraded component. But of course, this action preserves the ideal, because all I've done is a change of basis. However, if you now look at the first column of this picture, what you see is none other than the linked ideal. The reason being that this 1x2 matrix that appears above it is exactly the part of the multiplicative structure, which 3 A1 to A3, that gets used in defining the differential D1 via the result of Ferran. Right? That this is the last vertical map. That this 1x2 matrix is the last vertical map in the ladder. So what you see is that if you look at the first column of this picture, you get the generators of the linked ideal. But what if I want to go on? Right? What if now let's see the linked ideal. I see a regular sequence x, y squared, z squared, and I want to link with that regular sequence next. Well, I can do the same thing. I just have to move that sequence down into the bottom bigraded component, this time acting by an appropriate element of GLB1. The action of GLB1 preserved this ideal. So let me do that. Right, and in the same ideal, right? The first column is still the ideal generated by x, y, z, y squared, z squared, but now I've moved the regular sequence I want to next use into the bottom piece. And now I look at the first row again. I look at the first row, and by the same argument, I see this is the linked ideal, because the 1x2 matrix that appears to the right is none other than the part of the multiplication wedge 3b1 to b3 that gets used in the last vertical map in the mapping column, the ladder. So what do I see? I see that after 2 steps, I was able to go from my original ideal, which was 1562, to a complete intersection. Okay. Now, I want to go through this demonstration one more time, but this time focusing on a different part of the picture. Right? So I want to ask this because I feel like already I've given a good answer to my question earlier, like why should one care about the higher structure maps just by doing this demonstration? But I also want to revisit this point once more, which is how do I know this last ideal is a complete intersection, right? And as I sort of mentioned before, the way to detect that this is a complete intersection by the higher structure maps is the presence of a unit in the multiplicative structure. This is an equivalent characterization of when a perfect ideal is a complete intersection, is when the multiplication from wedge 3, A1 to A3 is non-zero mod M. But right, the punchline is that all I've been doing this whole time is acting on this matrix by elements of GLA1 and GLB1. So if this entire 1/78 matrix was non-zero mod M at the end, it better have been non-zero at the start. And that it is. Right, so let's back up a step now and go back to the start of this whole operation, right? So here I had just the higher structure maps from my original ideal. And the first time I ran through this demonstration, I was trying to call your attention to what's happening at the bottom here, right? So at the bottom, you see the differential, and then after I decompose it and do these funny operations of GLA1 and GLB1, I just see linkage. But now I want to call your attention not to what happens at the bottom, but what happens up top. In particular, what happens with these units. Right. So for my starting ideal, the top two structure maps from W superscript 1 are non-zero mod M. So then when I decomposed it with the bigrading, right, I see them over here, right? But the idea was that, okay, let me go to the next screen. So this structure map being non-zero for A translates to one of the structure maps here being non-zero for B. The reason I've written ... there is just because there's actually multiple graded components in there, so I just didn't want to write down all of them. But somehow this whole process is just tracking the movement of this unit down this picture until it finally reaches either the second row or the second column, right? It starts out over here, and then by the end of the story, it ends up down here, which is to say in the multiplicative structure for A. Right? So although the first time we ran through this process, we were just staring at what happens with the differentials, but now you see the unit, the fact that this map is not zero mod M is a witness to the fact that sometime down the line, you reach a complete intersection. Okay, so the actual proof is something like, well, since you can do a general element of GLA1 or GLB1 will result in a regular sequence at every step, and a general element will be good enough to propagate the unit downwards as far as you need, basically. Okay, this proves half of the theorem, right? In some sense, right? So why do I say it proves half of the theorem? It proves half of the theorem because it says if we know that this structure, this 1/78 matrix is not zero mod M, then the ideal is Lichy. Which leaves the other half, which is why should this matrix be non-zero mod M? Okay. So if we go take a step back now, and right, these matrices also, but these 6x7 or 6x27 matrices, they have full rank mod M, in fact, or equivalently, they're surjective. You can, if you stare at them for a little while, you can see the units are scattered around in these matrices, but in fact, they're surjective onto R6. So why should this happen? Why should this be the case? So this is the other half of the theorem that needs proving, right? Because so far the demonstration shows you how once the units are present, you can use group actions to move them down, and these group actions translate to linkage. But the question which remains is why should the units exist in the first place? And for that, I want to talk first about what happens in the case of type Dn, which is to say 1n and 1, the well-known Gorenstein case. For the well-known Gorenstein case, the structure maps that you get from D2, so what I'm calling W superscript 2, there's only two components. It looks like this. This is for 1n and 1. Right, so here you have the dual of D2, and then here you have the multiplication. Right? But in the Gorenstein case, it's the reason you can tell that this matrix is going to be surjective is because the multiplication, F1 tends to F2 to F3 for resolution of the Gorenstein ideal identifies F1 isomorphically with F2 equal, right? So this n by n sum matrix here, this is an invertible sum matrix. So the Gorenstein case, the units come neatly packaged into this one block, and we don't really have to work so hard to argue their existence. It's just there. And then, by the way, like this is of course, as far as language is concerned, highly ahistorical. But Watanabe's original argument for why Gorenstein ideals are lychee basically observes that once you have so many units here, in the next step, they move to becoming units in the multiplication wedge to B1 to B2, which is to say, in the step afterwards, you get a drop in total Betty number, right? So you go from 1 n and a 1 to a Gorenstein ideal after 2 links that has fewer generators. This is, of course, the language is very different, but this is more or less the idea of Watanabe's original argument for why Gorenstein ideals are lychee. Okay, but the bad news is that looking at what happens for the Gorenstein case does not really give us much hints how to do it for the other cases, because the Gorenstein case just uses this very nice result that, well, for a Gorenstein ideal, this multiplication identifies F1 isomorphically with F2 dual, right? So it tells us, why is this n by 2n matrix have rank n mod maximal ideal? Well, because it has an n by n sum matrix sitting right there, n by n invertible sum matrix sitting right there. Unfortunately, if you look at the matrix written up top, which is the 6 by 27 matrix for my monomial ideal, it's hard to see where you should look for the invertible, like the invertible 6 by 6 matrix, right? I mean, it's there if you see it written out explicitly, but like if you're trying to prove it, where would you look? So the way that we work around this is actually to prove that this 6 by 27 matrix is surjective. Instead of finding a 6 by 6 invertible sum matrix, we show that it's just a part of a larger invertible 27 by 27 matrix. And what I've displayed here is an automorphism of the 27-dimensional representation of E6. This is 27-dimensional representation of E6 over R. Now, it's not just any old automorphism, because this is the part I'm not really going to explain, but in fact, what's happening here is that we are constructing the action of an R value point of E6. And that's somehow the idea behind the proof of why this 6 by 27 matrix has full rank, is because it's actually just the first 6 rows of the invertible 27 by 27 square matrix. So again, right, the purpose of me displaying this matrix is not to say stare at it, stare at the entries or anything like that. It's to give an indication of how this part of the proof works. But also I want to point out the necessary hypotheses, right? So let me now go back to the handwritten notes. So theorem. So this is now one of the technical backbones of the previous result, is that if I is perfect with Dinkin Betty numbers, then and F is minimal free resolution of R mod I, then for any choice of the map R generic to R for F, the maps WI are surjective. Right, so I do want to comment briefly on where both hypotheses are used. Right, where the hypothesis that, okay. So the latter one that it has Dinkin format is sort of apparent, because if it weren't Dinkin this way, I wouldn't have a finite matrix. This would just go on forever, and the argument would not work at all if this were not of Dinkin format. The more interesting point I want to talk about is where I use the assumption that I is perfect, right? And this whole story is one about free resolutions. So in terms of free resolutions, how can I characterize that I is perfect? Well, if I take F to be the minimal free resolution of R mod I being perfect means that the dual of F is the free resolution of the canonical module. And one of the important facts that's often overlooked of Wyman's whole construction is that he did it in the case of module formats as well. So for the dual resolution, there is another generic ring constructed by Wyman. You can pick structure maps, so in other words, a map from R generic to R, which for that resolution, the dual of the original one. And I claim that just as how the structure maps for F give me the first block row of this matrix, the structure maps, the dual resolution, the resolution of the canonical module, will give me the first block column. And it's together using the first block row and the first block column that one is able to reconstruct the entire square matrix. But that's the part that I'm not really going to explain how it works exactly. But I just want to at least point out, like, both hypotheses are definitely necessary. And if you remove either one of the two, the statement's not even, like, the proof doesn't work, but the statement's also not true. But there are examples of, like, the square of the maximal ideal. If you compute this higher structure maps, it goes on forever, and all of them are contained in the maximal ideal. So you don't have this theorem being true. Okay. But now I want to note some funny consequences of this. So a brief excursion to graded setting. So the vast majority of the results I talk about today are the local setting, but now I want to state something that we can deduce in the graded setting. So the way that these higher structure maps work, they can be, like, the way the map from R generic to R can be computed is by doing a inductive lifting process. And one feature of this is that you start out with a resolution that's homogeneous. So it's homogeneous with all the differentials are homogeneous at degree 0. You can actually pick structure maps in a way that are also homogeneous of degree 0. Which means that the previous theorem can be used as a result to forbid certain types of graded Betty tables. Right? So let me point that out. If f differentials of f are homogeneous of degree 0, it is possible to take Wi also homogeneous of degree 0. But notice, for example, W1 was a map from F1 plus F3 dual tensor wedge 3 F1 plus ... to R. And I won't tell you what the later ones are impossible to write down explicitly. They get, well, impossible as for me to feasibly write down. But in every one, right, if this is the 0th graded component, then in the jth component, there are always going to be 2j plus 1 tensor factors of F1 and j factors of F3 dual. So here's an example. There are no perfect ideals satisfying all three of the following. Now this is graded setting. For example, graded polynomial ring. That I has Dynkin Betty numbers. And F1 is generated in all odd degrees. And F3 is generated in all even degrees. To also point out that the Dynkin condition is necessary because this is a valid Betty table. Like, you can actually have a Betty table that looks like this: 2, 3, 0, 1, 2, 3, 1, 8, 9, 2. Right. So this Betty table has the property that F1 is generated in all odd degrees and F3 is generated in all even degrees, but 1892 is not a Dynkin format. Right? So why is this true? Well, it's because if you have these degree constraints on F1 and F3, then all of these components are generated in odd degrees. So just by degree considerations, it will be possible to define a higher structure map that's equal to 0 mod m. But that would be in contradiction with the previous theorem. Right. So this somewhat technical seeming result on the surjectivity of structure maps gives some amusing consequences to the graded setting, just by observing that in certain situations, you're forced to have the structure maps be in the maximal ideal by degree considerations. Okay. So now that I've stated one of the two main results, and I've given, I think, enough indication of how the proof sort of proceeds. Of course, a lot more details that are not revealed here. I want to point out one other thing, which I'm not going to prove. So going back to this result here, I want to pay close attention to W1. So also the structure map that I previously shown decomposed, like in the case of 1562, 1x78 matrix that I decomposed and studied carefully. So particular. So let's focus on W1, right? So some component of it is non-zero mod M, right? If I continue with the assumptions before, the I is a perfect ideal. Let's write down, so this representation of E6, 78-dimensional one, was F1 in the bottom, F3 dual tensor wedge 3, F1, and then the next component, there are actually 3 representations, irreducible representations, which I'm not going to write down, and there's one more, and there's one more. So this is the representation V omega 2 E6, sub D 8-dimensional. The extremal representations, this decomposition, are these. And by extremal representation, I mean it contains extremal weights of the 78-dimensional representation. And this picture that I've just drawn has a combinatorial description as well. This is the double cosets of the wild group of 3, the diagram E6, modulo, okay, and draw the diagram E6, and 2 colors. So blue, and I guess red is the color we usually use for this one. Actually, no, I have it flipped. It doesn't really matter that much, but just want to be consistent. So this is the group generated by all these reflections. This is the one, the subgroup generated by all the reflections aside from the blue one, and this is the subgroup generated by all the reflections aside from the red one. The reason for this is that these cosets index all the extremal weights in this representation, and then modding out by the action of this group will identify the extremal weights that reside in the same representation when I decompose it. Now, what does this picture show? I claim that there is a well-defined notion of a lowest structure map in which a unit appears. There is a well-defined lowest structure map in W1 that is non-zero mod M. Right, so the substance of this claim, right? So first thing is that the structure maps are not unique. Right? When I say structure map, I really mean you pick a map from R generic to R for a particular resolution. But as I mentioned before, this map is not unique. So the first concern is that maybe if you pick a different choice of structure maps, then the units appear in a completely different spot. The other concern is that if you look at this picture, also I forgot one more adjective, lowest extremal. The other concern is that if you look at this picture, maybe a unit appears here and the unit appears here. And the question is, which one's the lowest? And I claim that, well, in order for a unit to appear here and here, it must also appear here or down here. So there's actually a well-defined notion of lowest always. So this claim I'm not going to justify, but if you believe this claim, then if I hand you an ideal, a perfect ideal of format of Betty numbers 1562, you can compute its higher structure maps, look at the lowest structure map in W1 that's non-zero mod M, and see what that translates to about the ideal. And this is now I'm finally ready to state the second main result, the theorem classification of Dynkin perfect ideals. Right, here's the statement. Suppose 1, B1, B2, B3 is Dynkin. Then I claim that there exists a family of perfect ideals of grade 3 inside a polynomial ring of some number of variables localized with an maximal ideal with Betty less than or equal to 1, B1, B2, B3, indexed by this double coset picture. Generic in the following sense. You take any perfect ideal up to those Betty numbers, then there exists a unique one of these generic examples such that there exists, but this part, the map that we do not require to be unique, exists the map from this polynomial ring. It's a local homomorphism to R specializing IW to I. And by the way, since these are both perfect ideals, this also means that if you take a free resolution of IW, then it specializes to a free resolution of I. Okay, so I'm going to end by just showing you what this picture looks like for two familiar cases. So I claimed in my abstract that this theorem is supposed to be an analog of the celebrated Boussoum-Eisenbud theorem for Gorenstein ideals of codimension 3. In the case of 1n and 1 corresponds to the Dinkin diagram Dn. So example, what is the classification of perfect ideals with Betty numbers up to 1n and 1? Oh, so I lied slightly. It's really, okay, I'm not going to bother correcting this, but it's really indexed by this thing minus the bottom node because the bottom node is kind of fake. But let me write this down now. The double coset picture for this is just a totally ordered picture that looks like this. Right, and remember, what is this supposed to correspond to in this picture? The idea is that this classification is based off of where a unit appears in the higher structure maps. So if a unit appears in here, which is say D1, then okay, it's just a unit ideal. Right? So that's why I'd say the bottom one's fake, because it's actually just a split exact complex. It doesn't really count for the classification. What does it mean for a unit to appear here? Well, we already talked about this, right? A unit appears in wedge 3F1 depth 3 exactly when it's a complete intersection. So this one is 1, 3, 3, 1. And you can sort of take a wild guess as to what the remaining ones are. The remaining ones are the generic examples of all the Gorenstein ideals in between 1 and 1 and 1. Right, this is also the reason why the statement is written with a less than or equal sign, because with a less or equal sign, I can more cleanly state it in correspondence with a double coset picture. So, and so on. Right, so this, what I'm not showing you is what these ideals explicitly are, but I claim that the construction also recovers the actual theorem, which is that this particular ideal is generated by the factions of a Imbainski matrix. Okay, now let's do one more example, just the 15621 one. The example, less than or equal to 1562. The double coset picture looks like this. All right, so again, the bottom one is fake. It doesn't really count. The next one is complete intersection. The next two correspond to 1551 and 1452. Okay, so both these are the generic examples of these types. The Gorenstein ideal on 5 generators and an almost complete intersection of type 2. The next two are both of type 1562. So what's the conclusion? The conclusion is that there are two types of perfect ideals of Betty with Betty numbers 1562. So let me write this down now. So both of these generic examples of Betty numbers 1562. And how do you distinguish them? Well, linkage actually gives a nice way. So these are exactly the ones that are linked to 1452. And these are the ones which are not. You can also characterize this in terms of the multiplicative structure, because remember, what does it mean to be linked to be able to be linked to lower Betty numbers? It means that there's units in the multiplication wedge to F1 to F2. So this is i.e. Multiplication on Tor is non-zero, and this is multiplication on Tor is 0. And this is studied in the paper. Max Wyman 20. Right, in the paper they say we expect this family of 1562 perfect ideals with zero multiplication on Tor to be important for the classification. And now here we have the precise answer, which is that there's only two types: the 1562 perfect ideals, those which are which have this zero multiplication property, and which are those that don't. And I say that there are only two types in the sense that there is a generic example for each type. Okay, so I think that's where I want to end for today. Thank you very much for your attention. And please let me know if you have any questions.
All right. Well, thanks so much, Xianglong, for the very nice talk. Any questions?
You gave a reference to a linkage result of Ferran and Pesquin's Barreau.
Mhm.
Is that only true for regular rings?
I believe that's true when R is just Gorenstein. But if someone with more knowledge wants to correct me, go ahead. But I think Gorenstein is good enough.
Okay.
But the main reason for if you're asking like because like I started out by imposing that it'd be regular, it's mostly because the main setting of interest when you want to actually talk about perfect ideals is when the ambient ring is regular. Because I mean, if you're not working with a regular ring, there's no guarantee that the projective dimensions are even finite, right? Or that. So I mean, somehow it's like well, you still make this work. You can just say that, well, you specifically look at those ideals with a free resolution of like 3, but somehow like the main case of interest is when the ambient one is regular ideal. If you want to apply all this like theory about finite free resolutions.
Okay, thank you.
I do have a question too.
Mhm.
So the theorem you just mentioned about by Ferran actually is generalized to linkage of modules in a paper of Martin Skolsky and Strucker.
So is this like Buchs-von Rim linkage?
Yeah, so it's a paper from 2005 by Martin Skolsky and Strucker, and they propose a definition of linkage of modules, and one of the results they have there is a module version of this result.
Okay.
So I was wondering if any of these techniques that you presented today have been used to study free resolution of modules?
So the answer is yes and no. So if that notion of linkage of modules is like coinciding with the notion of Buchs-von Rim linkage that I'm thinking of, then there is indeed a way of adapting these methods to show similar results for module formats with that notion of linkage. I'm not sure if that is the notion of linkage that you're thinking.
I don't know. Like there are several different notions of of linkage of modules, and the part of that paper doesn't seem to mention Buchs-von Rim complexes. So I don't know if it's the same notion.
I see. Okay, yeah. So I guess my answer is that if it is Buchs-von Rim linkage, then we expect that these similar techniques can be adapted to that. Yes. Yeah.
Thank you.
I think Yoja has a question or comment.
Yeah, I just wanted to say that I think this Martin-Skolsky-Strucker linkage is not what we call Buchs-von Rim linkage. At least I don't know the relation. Okay, yeah.
Okay, any other questions? Okay, well, thank you once again, Xianglong, for the talk, and thank you all for coming.
Thank you for having me.